Hello students, and welcome to this 8th lecture of the heat transfer course EEAQ 3235. Today we are having a look at heat transfer in extended bodies, and particularly for fins with an insulated end. So for a fin that has an insulated end, we have at x to 0, theta is equals to theta naught. At x is equals to L, there will be no heat loss to the atmosphere, so it means that d theta by dx will be equal to 0. And we last time came up with a general solution. Theta is equals to C1 E mx plus C2 E minus mx. So let us differentiate the above equation with respect to x. D theta by dx is equals to C1 m a mx plus C2. There is a minus, so E m E minus m x. So this becomes a minus. So now at x is equals to L, d theta by dx is equals to 0. So 0 is equals to C1 E ml minus, there is an m, C2 m E minus ml. And we've seen that at x is equals to 0, theta is equals to theta naught. So we have theta naught is equals to C1 E0 plus C2 E0, which implies that theta naught is equals to C1 plus C2. Now, so from that equation we can see that C1 is equals to theta naught minus C2. So this implies that from our first equation, that is 0 is equals to C1, but C1, from that we can say that C1 m EML is equals to C2 m E minus ml. So we have C1 is equals to C2 m E minus ml divided by m E ml. So the m cancels out. We are left with C1 is equals to C2 E minus ml over E positive ml. So we can say that from that equation there, call it equation 2. From 2, C1, which is C2, E minus ML over E ML is equals to theta naught minus C2. Okay, so from those two equations, we can say that C2 into bracket 1 plus E minus ML over E ML, that is equals to theta naught, such that C2 is equals to theta naught times E ML divided by E ML plus E minus ML, and that is our equation 3. Give us theta in general is equals to C1 plus a theta naught EML over EML plus E minus ML. That is theta naught is equals to that. So it means that a C1 is equals to theta naught into bracket 1 minus EML divided by EML plus E minus ML. So C1 is equals to theta naught E raised to the power of ML plus E raised to the power of minus ML minus E raised to the power of ML all over E to the power of ML plus E raised to the power of minus ML. So C1 is equals to theta naught E minus ML divided by EML plus E minus ML. And that is our equation 4. So now armed with C1 and C2, we can substitute C1 and C2 in our general equation, and we'll get theta is equals to theta naught E minus ML over EML plus E minus ML times EMX plus theta naught, okay, EML E minus MX divided by this one divided by EML plus E minus ML. So we can say that theta is equals to E minus ML E raised to the power of MX plus EML E minus MX divided by EML plus E minus ML. Theta is equals to E raised to the power of M x minus L plus E M L minus X all over E M L plus E minus M L, such that now theta divided by theta naught, that is by dividing both sides by theta naught, is equals to E M L minus X minus E minus plus E minus M L minus X divided by E M L plus E minus M L. Remember that we had M X minus L. So to make it compatible with this, we put a negative sign there, and then we get L minus X. But E raised to the power of X plus E raised to the power of minus X divided by 2 is cos hyperbolic of X, and E X minus E minus X over 2 is sine hyperbolic of X. So let us first of all put our above equation as E M L minus X plus E minus M L minus X, all of that divided by 2. Again, we have E M L plus E minus M L, all of that divided by 2. And you can see that a theta over theta naught is equals to cos hyperbolic of L minus X divided by cos hyperbolic of ML. So that will give us our temperature distribution, i.e. T minus Ts, T naught minus Ts is equals to cos L minus X divided by cos ML. This implies that T minus Ts is equals to T naught minus Ts cos L minus X over cos ML, differentiating, you get dt with respect to x. Dt by dx is equals to T naught minus Ts, which is a constant, d dx of cos L minus X divided by cos ml. So dt by dx is equals to t naught minus ts the derivative of cos, that is cos hyperbolic L minus x, is minus sine hyperbolic L minus x. No, it is sine hyperbolic L minus x, but because of this negative x there, we'll get negative there, divided by cos ml. Now, our rate of heat flow Q is equals to minus Ka dt by dx according to the Fourier's equation. But since dt by dx is a variable, we can decide to evaluate that at x is equals to 0, and we'll get our rate of heat of flow. So now, at x is equals to 0, dt by dx is equals to t naught minus ts, and there is a negative sign, and then we have sine hyperbolic of L, since x is equals to 0, divided by cos hyperbolic ml, and there is a name here, so we have a name somewhere there, we have a name there. Okay, so now it is equals to minus m t naught minus ts sine hyperbolic of ml over cos hyperbolic of ml, and sine hyperbolic of ml divided by cos, or cos hyperbolic ml, will give us tan hyperbolic of ml, and this will give us a rate of heat flow that is equals to minus Ka times m, and there is a minus t naught minus ts tan hyperbolic ml. Q is equals to minus K, minus and minus cancels, and we are left with K am T naught minus Ts tan hyperbolic ml. So this is equals to Ka, but m is equals to the square root of hp over Ka times T naught minus Ts tan hyperbolic of ml. So this is equals to a root of Ka hp times tan hyperbolic ml times theta naught. Now let us have a look at the last case where the fin is of a finite length and losing heat at its end. So for that case we have and that is our temperature distribution. So it is a smooth curve up to that point, then it suddenly becomes steeper at the end there. And at this position there, our Q is equals to minus KAC dt by dx, evaluated at x is equals to L, and it is equals to the heat that is being lost to the surroundings, which is HA, TA minus TS. H surface area, that is surface area. This is cross-sectional area, and that is the surface area. Now for this particular case, the boundary conditions are at x is equals to 0, theta is equals to theta naught, 2, heat is conducted to the surroundings at x is equals to L, and that is the heat convected from the end to the surroundings. So we have minus KAC dt by dx, evaluated at x is equals to L, is equals to HAS T minus TS. But one thing we should note is that at the tip of the fin, the cross-sectional area is equals to the surface area that is convecting heat to the atmosphere. So if that is the case, it means that the A's cancels out. We are left with a dt by dx is equals to, that is at x is equals to L, is equals to minus h theta divided by k. So applying the boundary conditions, we get a C1 for the first boundary conditions plus C2 is equals to theta naught. So it means that because we know theta is equals to C1 EMX plus a C2 E minus MX, then dt by dx, which is the same as d theta by dx, is equals to C1M EMX minus C2 ME minus MX. So at L we have theta is equals to C1 E ml plus C2 E minus ml. So, but theta is equals to T minus Ts is equals to C1 E mx plus C2 E minus mx. So d theta by dx is equals to dt by dx is equals to C1m E mx minus C2m E minus mx. Okay. At x is equals to L, we have dt by dx is equals to minus h theta r over k, which is equals to C1 m E m L minus C2 m E minus m L. But from the general equation, theta is equals to C1 E mx plus C2 E minus mx. So at x is equals to L, our theta will be equal to C1 E ml plus C2 E minus ml. So we can say that from this equation, equation 2, minus h over k theta, but now theta is C1 E ml plus C2 E minus ml must be equal to C1 m E ml minus C2 m E minus ml. Dividing through by m, we have h over km minus C1 E ml plus C2 E minus ml is equals to C1 E ml minus C2 E minus ml. Now we have from the first boundary conditions, C2 is equals to theta naught minus C1. So we can substitute for theta 2 in this equation, C1 E ml plus C2, and C2 is theta naught minus C1 E raised to the power of negative ml is equals to C1 E ml minus theta naught minus C1, which is C2 E minus ml, and that is our third equation. From this we can get C1 is equals to theta naught 1 minus h over km E minus ml divided by EML plus E minus ml plus h over km E ml minus E minus ml And by the same analysis, we can get C2 is equals to theta naught minus theta naught 1 minus h over km E minus ml divided by EML plus E minus ml plus h over km EML minus E minus ml. And from those two equations, that is for C1 and C2, we can get our theta over theta naught is equals to T minus Ts divided by T naught minus Ts. And you can get it as cos ml minus x plus h over km sine hyperbolic ml minus x divided by cos ml plus h over km sine hyperbolic ml. And that is what I've given in your assignment, to come up with this equation from where we left it at, and also to show that a Q now for the fin is equals to the square root of PHKA times theta naught times tan hyperbolic ml plus h over km divided by 1 plus h over km tan hyperbolic of ml. So let us have a look at an example there, example 1, which reads: an electric motor drives a centrifugal pump which circulates a hot liquid metal at 480 degrees C, and the motor is coupled to the pump impeller by a horizontal shaft whose material has a conductivity of 32 watt per meter Kelvin. The shaft has a diameter of 25 millimeters, and you're told that the ambient temperature is 25 degrees, is 20 degrees. You're told the temperature of the motor is limited to 55 degrees. The heat transfer coefficient between the shaft and the ambient air is 14.8 watt per meter squared Kelvin. it is required of us to determine what the length of the shaft is between the motor and the pump. The solution is now theta over theta naught T minus Ts over T naught minus Ts, because we will assume the shaft to be a fin with an insulated end, divided by cos hyperbolic of ml. So we have 55 minus 20 divided by 480 minus 20 is equals to, remember that we are evaluating this at x is equals to 0, so this becomes cos at 0 at x is equals to L. So we'll have cos hyperbolic of 0, which is 1, cos hyperbolic of 0, which is 1 over cos hyperbolic of ml. So it implies that cos hyperbolic of ml is equals to 13.14, such that ml is equals to 3.267 from the tables. But we know that m is equals to hp over ka square root. So this is equals to h times pi d as our perimeter times h, k times pi by 4 d squared square root, which is equals to pi and pi cancels out, so we have 4h divided by kd square root. So this is equals to 4 by 148 divided by 32 times 0.025 square root, which is equals to 8.6 per meter. So it means that 8.6 times L is equals to 3.267, such that L is equals to 0.3799, which is approximately equal to 0.38 meters. Let us have a look at another example. Example 2, that reads at some turbine blades made of stainless steel, K is equals to 229 watt per meter Kelvin, is 60 millimeters long, 500 millimeters squared cross section, and the perimeter is equals to 120 millimeters. The temperature at the root of the bread is 480 degrees C, and it is exposed to the products of combustion passing through the turbine, and they are at 850 degrees C. We are told that if H between the blade and the combustion gases is 320 watt per meter squared Kelvin, determine A, the temperature at the middle of the blade, B, the rate of heat flow from the blade. So let us have a look at this solution. We have theta over theta naught is equals to, so this is a case of a fin that is losing heat energy at its end. So we have that as cosh ml minus x plus h over km sine hyperbolic L minus x divided by cos hyperbolic ml plus h over km sine hyperbolic ml. And we know that m is equals to the square root of hp over ka, so that is equals to 320 times 0.12 divided by 29 times 50 times 10 to the power of negative 6 square root, and this is 5.46 per meter, such that ml is equals to, this is 51.46 is equals to 51.46 times 0.06, that is 3.087. Let us also evaluate h over km, which is 320 divided by 29 times 51.46, which is equals to 0.214. So now at the middle, x is equals to L by 2. So we'll have T minus Ts over T naught minus Ts is equals to cosh ml over 2 plus h over km sine hyperbolic ml over 2 divided by cos hyperbolic ml plus h over km sine hyperbolic ml. So this is equals to cos hyperbolic 3.087 over 2 plus 0.214 sine hyperbolic 3.087 over 2 divided by cos 3.087 plus 0.214 sine hyperbolic 3.087. That you will get it as 0.219. Now at the midpoint, that is at t, at a midpoint 0.5 L, t is equals to T naught, which is 820, plus 0.214 times, now the temperature 480 minus 820, and that will give you a temperature of 745 degrees C. Now let us have a look at B. The rate of heat flow Q is equals to Ka M T naught minus Ts tan hyperbolic ML plus H over Km divided by 1 plus H over Km tan hyperbolic ML. So this is equals to 29 times 500 times 10 to the power of negative 6 times 751.46 480 minus 820 tan hyperbolic 3.087 plus 0.214 divided by 1 plus 0.214 tan hyperbolic of 3.087, and that will give you a figure of about minus 253 watts. Thanks.